Hello, my name is Jason Reed, and in this video I'll be presenting a previously published paper entitled Sequence-Aware Intrusion Detection in Industrial Control Systems. This presentation is being submitted as partial fulfillment of ECE 8813, which is a required course in the Cyber-Physical Systems track of Georgia Tech's cybersecurity program. This paper is on a subject that I am passionate about, but please note that I am not in any way involved in the original publication or research. The authors are acknowledged here, and their paper was originally presented in April of 2015 at the first ACM workshop on cyber-physical systems security. To give an introduction, industrial control systems, or ICS, operating on critical infrastructure are an attractive target when it comes to malicious behavior. Some attacks rely on knowledge of the control processes or even the systems being controlled to maximize the damage inflicted. This concept is known as semantic attack. Stuxnet is one of the most well-known examples of a semantic attack. The malware was designed to manipulate a specific type of PLC, or programmable logic controller, being used for a specific application. One type of semantic attack involves sequences of events. Most network intrusion detection systems look for unique, unusual, or unpermitted operations, but sequence attacks exploit the possibility to arrange valid events in a way that is problematic to targeted systems. One example might be rapidly opening and closing a valve, where an IDS sees both the open and close commands as normal traffic without any regard for the command sequence or frequency being potentially harmful. This paper outlines the development of a sequence-aware intrusion detection system that identifies patterns of ICS network events, extracts their semantic meaning, and models known behaviors over time. Finally, the authors test the system on a real ICS traffic samples set captured from a water treatment and purification facility. Just a quick review of what we mean by ICS. The term refers to a large variety of technologies, including supervisory control and data acquisition systems, distributed control systems, programmable logic controllers, and human-machine interfaces, all of which are a form of control, monitoring, or interface where commands are sent to or read from devices that interact with a physical process, like sensors, actuators, and RTUs. Now, for decades, the communication protocols used between various systems were mostly serial-based, but in more recent years, of course, they've been ported to the TCP/IP protocol stack. The author's research focuses on three different protocols, specifically Modbus, MMS, and IEC 104. And for the sake of time, I will not be going into these in detail, but just know that most of the paper is focused on Modbus, which is an application layer protocol commonly found in industrial control systems. Like most publications, this paper builds on research that came before it, and since it has a dedicated section outlining related work, I'd like to just briefly highlight a handful of key citations that span the evolution of intrusion detection systems. The first is a paper from 1999 cited for discussion on signature-based versus anomaly-based detection, but it contains a categorical overview of intrusion detection around the time when commercial products first had become available. And according to ResearchGate.net, this publication has been cited 722 times. One approach to anomaly-based intrusion detection is called specification-based detection, where the goal is to learn normal behaviors from the design specifications of a system or protocol. The main idea was to reduce false alarms, otherwise generated by traditional anomaly detection, and allow models of normal behavior to be reliably built without a learning phase. The authors of the paper note that specification-based detection can solve specific cases of sequence attacks, but the implementation relies on the presence of extremely accurate information as to how the system operates. Next is header analysis, which most anomaly-based IDSs at the time were focusing on port number and IP address information. In some ways, this is similar to firewall functionality, but at the time, any advancements that were efficient and avoided the complexities of deep packet inspection continued to garner attention. Flow-based intrusion detection profiles network traffic in terms of connections or properties of the traffic in order to identify unknown or malicious trends in the data. This addressed attacks that largely intended to consume bandwidth, something that signature-based detection and header analysis didn't really handle very well. The development of payload-based detection was when anomaly detection began to shift from header analysis to the payload itself. This publication by Wang and Stolfo has been cited 692 times according to ResearchGate.net. And it may be worth mentioning that the readings by these authors have been associated with one of the projects in Georgia Tech's CS 6262 course on network security. If you took that class, you might remember the PAL anomaly detection system. Next, there are works citing that cover advancements in payload-based detection, where we move from static analysis to include binary code extraction. And finally, there is discussion on other work involving detection of anomalies in discrete sequences or ordered series of events related to this paper. The field is of particular importance to industrial control systems, as previous approaches generally did not try to understand whether normal data or normal commands might be delivered in an abnormal or malicious way. So the authors propose an architecture based on a layered structure. Each layer receives information from a lower layer, evaluates them, and forwards the results to the following layer. The first layer is the reader, which oversees the capturing of raw information. These could be files, network packets, data streams, and generating a uniform format for the other layers. The reader also filters out redundant or corrupted data that will not be needed. Next is the sequencer. This layer oversees transforming of data flowing through the reader into a chronological sequence of events. Because this activity relies on a precise definition of what an event is, the event is defined by a set of rules used by the sequencer to organize information into formalized data units. So, for example, read messages could be considered one type of event, while write messages can form another type of event. Finally, the modeler is the last layer. This layer oversees reading of ordered events coming from the sequencer and builds models that represent how the system behaves over time. The detection layer uses a set of training models as a reference point and analyzes the differences with the detection models. This layer also manages alerts to users when malicious patterns are identified. The paper focuses on 2 reader instances to gather information from the network messages and log files, as well as 3 different sequencer instances to analyze ICS protocols, host log entries, and the behavior of process variables. Discrete time Markov chains are used to model sequences, and the detection mechanism computes weighted distance statistics among the chains based on probability of their transitions. As I mentioned, there are 3 different use cases for sequencing. First is network communication. The definition is as shown here, where a Modbus sequence is a time-ordered list of events where E is a tuple containing ID, code, and data derived from a sequence of message pairs. The ID is just a transaction identifier, and the code indicates the type of operation performed. And then, of course, data represents the information carried by the Modbus requests and responses. Next is log files, shown in definition 2, where a log file sequence is a time-ordered list of events where E is a tuple which can vary in length depending on the system, representing the attributes of a log entry and identifying an operation performed by a device. Finally, we have process variables, and a sequence of events related to a process variable simply describes how its value changes over time. Now, this next slide is quite heavy on definitions and terminology associated with the modeling algorithm, but don't worry, I have an example coming right after. So once we have established the event sequences, we can then create a model of our system using discrete time Markov chains, which I'll refer to as a DTMC model. The idea of a DTMC is to cluster events that share the same semantic meaning into the model state sequence. In the network communication case, this concept can refer to the involved commands or carry data. So for example, a DTMC state that gathers together all of the write commands that change a specific variable could be one. In the log file case, it's possible to cluster sequences of events that share the same identification code or deal with the same component. And finally, process variable case, the DTMC states can cluster values belonging to a specific interval. So for example, temperature values in the range of between 60 and 70 degrees. Now in the DTMC, we have states and we have transitions between those states. So for every event of a sequence, the modeling algorithm either needs to add the event to an existing state, indicated by the update s function shown on the right, or it creates a new state in a case where the event does not match the attributes of something that happened before in the model. This is indicated by the add s function shown. Additionally, the algorithm either adds or updates a transition function. A transition links the previous state to the current one. In this algorithm, these are the add t and update t functions. In our model, every state S is defined by a tuple consisting of data, type, number of elements found in the sequence that belong to S, first time seen and last time seen, which are just timestamps of the first and last elements associated with the state. Finally, every transition then from the source state to a destination state is defined by another tuple, including probability ratio, number of jumps from source to destination, first jump, last jump, average time elapsed between the states, and the standard deviation of time elapsed. Okay, so to illustrate how the DTMC modeling process actually works, consider the following sample sequence built on the Modbus network communication network scenario. In the figure, the first event of the sequence creates a DTMC state of type request response, representing Modbus messages used to read one coil from address 0. This is line 1 of the numbered list of Modbus transactions and state A in the diagram. The second element of the sequence creates another state in the model which has the same type attribute, but represents Modbus messages used to read 10 registers from address 100. This is line 2 of the numbered list and state B in the diagram, which is on the far right side, not the top. At this point, the model needs a transition between the two states that describes the sequential relationship between these two elements. This is transition 1, or T1, shown in the figure near the top of the slide. Next, the third element of the sequence, number 3 of the numbered list, actually has the same attributes as the first element, so this will increase the attribute called number of elements on the first DTMC state. A new transition connecting back state B to state A is now needed to show the new relationship observed in the sequence, noted as T2. Finally, element 4 of the sequence is part of state B since it has the same attributes as number 2 in the list. And because the model already has a transition linking these two states, the algorithm only increases the attribute called number of jumps on the transition that connects state A to state B. The other statistical attributes get updated as well, like average time elapsed, etc. Note that the diagram here shows the final state after number 4, which is why the number of elements and the number of jumps are already incremented to 2 in some cases. During the detection phase, we now search for unknown or uncommon patterns that are potential effects of sequence attacks carried out by the intruders. Targeted anomalies can be of 3 types: unknown state, unknown transition, unknown probability relates to Markov chain states and transition whose related probabilities differ with respect to the one detected during the training phase. While identifying these, the detection algorithm needs to avoid some false positives. Unknown but correct state refers to an unknown state anomaly caused by an event that is not dangerous for the system under control. And an unknown but correct transition relates to an unknown transition anomaly caused by a new link between two events that doesn't really interfere with the correct functioning of the system. So looking at these two lists, you might wonder why unknown probability can't be a false positive. The authors indicate that this metric is very robust, with false positives being quite rare, and the system should just always notify on unknown probability anomalies. In the detection phase, we evaluate differences between trained DTMCs and those built up during detection. Given a known state, the detection algorithm looks at its transition set and computes the difference between the probability values measured in the learning phase and real time. We handle transitions the same way, resulting in the two distances defined as shown on the right. Again, these values are based on probabilities, and the result of both equations is always in the range of 0 to 1. The detection procedure defines a threshold called theta, which, if exceeded in either equation, triggers an alert to the user. Now, if the threshold is too high, the accuracy of the IDS increases, fewer false positives, but its comprehensiveness then decreases, fewer or more false negatives. On the other hand, if the threshold is too low, the resulting high number of false positives is likely to make the IDS ineffective. The threshold value also depends on the nature of the environment in which the IDS is working. So control systems that show higher variability in the communication patterns will need higher thresholds. To improve the detection algorithm, we can use some information from the physical process. So there's three here. The first is event importance. Some messages, commands, and values are in fact more likely to be used in semantic attacks than others, so we can react differently if an anomaly relates to an important versus an unimportant event, and the system will trigger an alert on unimportant events only if the change is very high. Next is event semantics. This involves the analysis of anomalous states and transitions. So suppose we want to model the behavior of a variable that represents a temperature. States can be defined as intervals of n degrees. The state A could represent 0 to 10 degrees, state B 10 to 20, and so on. The value of the variable ranges, let's say between 0 and 100, then would have states assigned A through J, as seen in the figure shown on the right. Now let's suppose that during the detection phase, two anomalies are present, leading to two new transitions in a detection model, seen as the red arrows in the figure. According to the detection algorithm in its most basic form, these two anomalies have the same detection score and are equally concerning. However, the two transitions are in fact quite different in meaning, as one concerns a temperature increase of anywhere between 11 and 20 degrees, while the other is an increase of close to 100 degrees. The first anomaly might be explained by an imprecise sensor reading or even a delay in the update of the variable's value, whereas the second anomaly should be more concerning and thus given more weight. Lastly is transition timing. Transitions with low variability often relate to automated behaviors of control processes, while transitions with high time variability can involve the effect of human behaviors, and these types of anomalies might justifiably be filtered out during the detection phase. Putting it all together, the approach is tested on data coming from a water treatment and purification facility using Modbus communication. First, we want to evaluate whether the detection approach might generate too many false positives. Then we introduce some artificial data into the trace to show the effectiveness against attacks. The figure shown represents the result from our modeling approach applied to a communication involving a PLC and a SCADA server over 4 hours' time. Most of the Modbus connections involve just one or two Modbus requests or responses sent periodically. Connections between PLCs and the SCADA server expectedly have a higher variety of messages. Most of the transitions have low probabilities. These are the thinner lines in the diagram you see here, while a small set of them have a probability greater than 0.9, forming a clear path through all states of the model. These are the thicker lines. The detection algorithm is run against a single day of traffic captured on the network, and the threshold theta is minimized to 0.1 to alert any significant change within the transition probability sets. No malicious traffic is included in the data set at first, therefore the test merely verifies detection resilience against false positives. The SIDS raises 211 alerts at a rate of 1 alert approximately every 40 minutes. Remember, theta was set to only 0.1, and it's worth noting that 96% of the false positives are generated by a new transition due to a network delay that was associated with just one of the connections between the PLC and SCADA server. Two attacks are performed. First, we invert two write messages concerning the control of two different pumps. Second, we trigger several start and stop commands on the same pump. Now, due to the criticality of the water treatment facility, the authors were not allowed to test the attacks on the actual network. For this reason, they replay the same 24 hours of real traffic plus the attacks and send it to the intrusion detection system. The first attack causes the presence of two new transitions. The second attack causes two anomalous states, a new transition, and three anomalous transitions with substantial change in the probability, particularly one transition that now links the start event with the stop event at a probability which increased from almost 0 to now 99%. Next, we define as important any command and write operation observed in the communications and assign them a value of importance equal to 1, and repeat the two tests discussed earlier. Within the 24 hours of clean traffic, the SIDS raises just 9 false positives instead of the 211, with a rate of 1 alert every 2.5 hours. When adding the malicious traffic, we get 17 alerts, 8 of which were identified before as effects of the sequence attacks and are now confirmed with the enhanced detection. So the enhancement techniques mentioned earlier indeed have a notable effect on the reduction of false positives. To summarize, this paper discussed sequence attack scenarios within industrial control systems and presented an approach to the development of a sequence-aware intrusion detection system. A layered architecture was proposed encompassing in-depth analysis of ICS data and leading to a comprehensive description of device behavior over time. The approach was tested using real-world data traces gathered from a water treatment and purification facility, and it was shown that the SIDS can correctly identify sequence attack instances as well as keep the number of false positives low. I do have just one criticism that I'll offer in a constructive manner for any fellow students who might perform similar research in the future. The authors used network traffic from a real-world example of critical infrastructure, but then they invoked simulated attacks by adding command messages to the recorded network traffic. This was due to the critical nature of the water treatment facility, which makes sense. However, the results may not properly account for the plant response to the malicious commands. For example, a feedback run indication from a pump that was just instructed to start would be missing. However, the authors do a good job of explaining the nature of the attack messages as well as the anomalies identified, particularly the probability of transition between start and stop, which went from near 0 to 99%. This was a convincing result that's clearly associated with the frequency of commands introduced and not the plant response to them. Still, a more solid approach might have been to build a simulation of the plant or some portion of it. Then the attacks could be invoked on the simulation as well, which would then capture the plant's response to the malicious commands and further validate the findings. In contrast to this one criticism, I must also praise this research for something that the authors never even acknowledge or take credit for. Now, certainly the focus of the paper was on intrusion detection, but I find it important to note that in the form of an anomaly detection system, not just IDS, this work offers even more value because it could be leveraged to better understand operational issues that have little to do with cyber attacks. For example, many industrial facilities suffer from control room alarm flood, where dozens of or hundreds of alarm conditions can seemingly be triggered around the same time. In situations like this, just looking at the very first alarm that came in is not always very telling. But if my operation had a sequence anomaly detection system that flags some sort of normal event that happened out of sequence or otherwise happened in some abnormal way at a time when a series of alarm conditions were triggered, that information would be extremely valuable to me in terms of root cause analysis. Altogether, I thought this was an excellent advancement in the way we approach semantic attacks and monitor abnormal event sequences. Quickly, I'll display here just a couple of other more recent papers that came after this work. The first outlines the various families of IDS approaches, and this is nearly 2 decades after that first taxonomy reference I talked about at the very beginning, but now with a focus on ICS. The second involves detection strategies to cope with proprietary binary protocols, which are often found in large industrial facilities. These are protocols that are not open or standardized, and they present yet another challenge in applying a traditional detection algorithms to the field of industrial control. If you made it to the end of this video, I'd like to thank you for the time you invested. If there is one takeaway I'd like to reinforce, it is that industrial control systems do face challenges that information systems do not, and sequence attacks are a very stealthy and noteworthy threat to critical infrastructure. Thank you.